Hello and welcome. Today, we are going to pull back the curtain on a topic that is absolutely essential for understanding modern medicine: biostatistics. We're going to break down the key ideas you need to really truly understand a clinical study so you can tell the difference between solid evidence and, well, just noise. Let's jump right in.
So let's just admit it right up front. The word statistics can be a little intimidating, can it? It might even give you flashbacks to a really tough math class. But I promise you, stick with me here, and you'll start to see it less as something to be scared of and more as an incredible tool for finding the truth.
So, why do we even need to talk about this? Well, because biostatistics is the very bedrock of evidence-based medicine. It's the rulebook, the objective system we use to figure out if a new treatment, a new drug, a new intervention, if it actually works. Without it, we're just guessing.
When you boil it all down, biostatistics is really just a method. It's a structured process that lets us take all this messy, complicated information from the real world, from patients, from labs, and turn that raw data into knowledge we can actually trust and act on.
And this gets us to the absolute heart of the matter: variability. Think about it. No two people are the same, right? Everyone responds a little differently to medication. Their symptoms aren't identical. There's just so much natural variation. Biostatistics is the science that gives us the tools to manage all that variability and find the real, meaningful signal that's hiding in all that biological noise.
So that leads us to one of the most fundamental challenges in all of research. It would be great to study every single person on the planet with, say, high blood pressure. But that's impossible, right? So we have to get a little bit clever. And here's the clever bit. We have the population, which is the entire group we care about. The true answer we're looking for in that group, like the actual average blood pressure of every single person with hypertension, is called a parameter. But since we can't measure that, we take a sample, which is just a smaller, representative slice of that population. And the number we calculate from our sample, that's called a statistic. So the whole game is using the statistic from our sample to make a really good, educated guess about the true parameter of the whole population. It's an estimate, but a powerful one. Okay, so we've got our sample, but what exactly are we measuring? Well, the things we measure that can be different from person to person are called variables. And trust me, figuring out what type of variable you're dealing with right at the beginning, it is absolutely critical. Get this wrong, and the whole study is built on a shaky foundation.
First up, we've got qualitative variables. The name kind of gives it away, right? These describe a quality or a category. Think of them like labels or tags, not hard numbers.
Now we can split these into two types. First, there's nominal. These are categories with no natural ranking. For instance, the cause of a disease could be an infarction or an arrhythmia. One isn't higher than the other, they're just different. Then you have ordinal variables. These do have a logical order. A pain scale from 1 to 10, or disease severity ranked as mild, moderate, severe. You see? There's a clear progression there.
And this right here is a huge, huge warning. It's a trap so many people fall into. With an ordinal scale, like that pain scale, you know a score of 8 is worse than a 4. But you cannot say it is twice as much pain. The gaps between the numbers aren't mathematically equal. It's just a ranking. Confusing this is a major error when people read studies.
All right, let's look at the other side of the coin. These are the variables that are all about the numbers, the quantitative variables. These are the things you can actually, measure.
And these also come in two main flavors. We've got discrete variables. These are basically counts, things that can only be whole numbers. You can have 2 or 3 children, but not 2.5, right? You can spend 4 days in the hospital, not 4.2. Then you have continuous variables, which can be any value in a given range, decimals included. Think about things like your weight or your blood sugar level. Those can be incredibly precise numbers.
So now we know the language of data. How do we actually build a study that's going to give us answers we can trust? This is so important. This isn't something you figure out after the fact. Your statistical plan has to be absolutely rock solid before you enroll a single patient.
And there are two pillars here that are completely non-negotiable. First, random selection. To get a sample that truly represents the whole population and to avoid any bias, you have to choose people at random. Second, sample size calculation. You absolutely must figure out beforehand what the minimum number of people you need in the study is to have a shot at finding a real answer.
But what's the big deal?
I mean, really, what happens if you just kind of wing it and your study ends up being a little too small? Well, what happens is the study becomes what we call underpowered. And this is a catastrophic failure. It means you might not have enough statistical oomph to see a real effect, even if it's there. You could test a drug that actually works, but because your study was too small, you mistakenly conclude it does nothing. It's a total waste of time and money, and even worse, it could stop a good treatment from ever reaching patients.
Okay, so let's say we've designed our study perfectly, we've collected all our data, now what? Well, this is where statistics really does its work, and it basically has two main jobs: describing what you found, and then making a big leap to what it might mean for everyone else.
I really love this analogy. Think of descriptive statistics as just taking a photo of your data. You're just showing exactly what you see in your sample. Here are the averages, here are the charts. Simple. But inferential statistics, that's where you make a leap. You use that photo of your sample to make an inference, an educated guess, about the entire population. This is where you really test your ideas using tools like the famous p-value.
Ah yes, the p-value. You see p is less than 0.05 everywhere, but what does it actually mean? Well, think of it as the flukometer. It answers this one question. If there was actually no real effect at all, what's the probability that I'd see a result like mine, or even more extreme, just because of random chance? So a really small p-value, like less than 0.05, tells you that it's pretty unlikely your results are just a random fluke. It suggests something real is probably going on.
Now, all of these tools, all of these concepts, they are unbelievably powerful. But, and this is a really big but, it is so important to remember that statistics is a tool. It is not magic. And just like any tool, it has its limits.
And that's where this idea really hits home. Statistics provides evidence. It tells you about probabilities, it supports decisions, but it never, ever makes them on its own. That's where the wisdom, the experience, the clinical judgment of a real health professional comes in. That part is absolutely irreplaceable.
And if you take away only one thing from this whole explainer, let it be this. You can run the most brilliant, sophisticated statistical analysis in the world, but it cannot rescue a poorly designed study. If the setup was flawed, if the data was collected badly, it doesn't matter. It's garbage in, garbage out. Always.
So I want to leave you with a question. The next time you pick up a medical study, what are you going to look for? Are you going to check how they pick their sample? Are you going to look to see if they justified their sample size? Will you think about whether they're using nominal or ordinal data correctly? Asking these questions, that's the first step to becoming a truly critical and informed reader of science.